Okay. Hi, everyone. Welcome back. It's been a while. Good to see you all. So today we are very happy to have Mikhail Ostrovskii, and he's speaking on Dvoretzky-type theorems for locally finite subsets of Hilbert space. Mikhail, take away.
Okay. Thank you very much for your invitation. And does everyone hear me and see what I'm showing? Okay.
Yes.
Okay, then I shall start. So the title is Dvoretzky-type theorem for locally finite subsets of a Hilbert space. It is joint work with Florian Katrina and Mikhail Ostrovskii. It is supported by the grant listed there. And so let me start. So let me recall the classical Dvoretzky theorem, which was announced in 1959 and published in 1961, and which proved Grothendieck's conjecture, which he made in 1953. So Dvoretzky theorem, it is as Dvoretzky stated it in section 7 of his paper. So let K be a positive integer. This restriction K is at least 2 is not really necessary. For K equals 1, it is also true. And epsilon between 1 and 0, then there exists such big positive integer so that for every norm space having more than n dimension, in particular every infinite dimensional norm space, has a k dimensional subspace whose Banach-Mazur distance from the k dimensional Hilbert space is less than 1 plus epsilon. Dvoretzky does not have words Banach-Mazur. I inserted them. So in this connection, in connection with this result, it is natural, in our opinion, to call a result establishing significant presence of Hilbert space structures in an arbitrary infinite dimensional Banach space a Dvoretzky-type theorem. And now let me recall some well-known definitions. So a metric space is called locally finite if each ball of finite radius in it contains finitely many elements. A map between two metric space is called a bi-Lipschitz embedding if it is somehow bounded from above and from below. And the distortion here, I don't provide exact definition, but it is the product of Lipschitz constant and Lipschitz constant of the inverse. And a bi-Lipschitz embedding whose distortion does not exceed C is called C by Lipschitz. And finally, an embedding which preserves distances is called an isometric embedding. So the main result of this talk is to prove the following Dvoretzky-type theorem, that given any epsilon, every locally finite subset of L2 admits a bi-Lipschitz embedding into an arbitrary infinite dimensional Banach space. It is similar to Dvoretzky theorem, but now instead of finite dimension of subspace, we have a locally finite set. So it is the statement of the main result. And I would like to mention that here one cannot require isometric. It is easy to guess, and in a paper with Ostrovskii in 2019, we constructed example. For example, for LP, you can construct a locally finite subset of L2, which does not admit isometric embedding into LP. And of course, finite subsets of L2 that admit isometric embedding into LP, it is a well-known fact. And at this point, it is appropriate to present a short overview of the available Dvoretzky-type results and related open problems. So first, we recall the open problem on the validity of finite isometric Dvoretzky theorem for all infinite dimensional Banach spaces. It is the following problem, which I had asked in 2015. Do there exist a finite subset of L2 and an infinite dimensional Banach space such that F does not admit an isometric embedding into X? If someone will get a positive answer to it, it would be a very surprising from my perspective. And it will be a strengthening of Dvoretzky theorem, because it would imply Dvoretzky theorem almost immediately using some ultra products. So it is an open problem. I suggested it in 2015 on overflow. And also there, somewhat later, I suggested similar question for Krivine theorem. But that question for Krivine theorem, we answered, and it turned out to be not really difficult. So it is a related result proved by James Kilbane and myself published in 2018, that for each P in that range, in reflexive range, except 2, there exists a subspace isomorphic to LP and a finite subset F of LP such that F does not admit an isometric embedding into X. It is a similar question to the problem, but it is a kind of, that is analog of finite Dvoretzky theorem. This would be finite isometric Krivine theorem, because Krivine, from results of Krivine, it follows that if you have something isomorphic to LP, then LP is finitely represented in that space. And it would be an analog, isometric analog, isometric strengthening of that, but it turns out not to be true. So now, before proving this result, which is main result of the paper, much earlier, I proved some weaker result. In 2006, I proved that each locally finite subset of L2 admits a coarse embedding. It is far from being 1 plus epsilon by Lipschitz coarse embedding into arbitrary infinite dimensional Banach space. Then, using technique of Badier-Lancienne, paper which was published in 2008, which is different from what I used in 2006, this result was strengthened to the following. So it is coming closer to Theorem 1. Each locally finite subset of L2 admits a by Lipschitz embedding into an arbitrary infinite dimensional Banach space. And in 2009, it was clear that the constant is not really small in that proof. I did not try to give an estimate for the distortion. It is some number of that proof. It is some number below 100, but not really far from it. And now I did not want to spend time on checking what constant I would get in 2009. So I just say that it is some number below 100 and not far from it. And of course, Theorem 1, because isometric result does not hold, and which is easy to guess, which is, I think that in addition to that example, which we constructed, one can construct others too, for that particular case. And Theorem 1, of course, is the best possible result in this direction. Now, I would talk about failed, what I would consider Dvoretzky-type theorem, but which failed. And as another development, Piotr Nowak in 2006 showed that the embedding techniques of Daderlat-Güntner can be used to construct coarse embedding of Hilbert space into Banach spaces for which such an embeddability appeared to be somewhat unexpected. And later, slightly later, I combined this technique of Nowak with the results of Odell and Schlumprecht on, this is a paper in Acta Mathematica in 1994 on the distortion problem, where they proved very strong results on homeomorphisms of unit spheres of Banach spaces. And I used that result and strengthened Nowak's result as follows. So if X is a Banach space containing a subspace with an unconditional basis, but that without L infinity uniformly, then L2 embeds coarsely into X. And of course, it is not the only space into which it embeds. coarsely. Of course, it embeds coarsely into C0 and any space containing C0. It is by result of Aharoni. So it was a kind, on one side, we have that spaces which are a kind of far from L infinity, and it contains it. And on the other hand, it also contains, it can be embedded coarsely into C0. And so it was natural to check whether one can get following common generalization of two of the mentioned result of this result together with Aharoni theorem and the result which I mentioned before, that locally finite subsets of L2 embed coarsely into any Banach space. So it was natural to ask question, is it true that L2 embed coarsely into an arbitrary infinite dimensional Banach space? And so I repeat here this problem, and this problem was posed by me in 2006 and repeated in 2009. And then it was repeated both by me and some other authors several times. A positive answer to this problem would be a very impressive Dvoretzky-type theorem. But as a matter stands, it was answered in the negative by Badiel, Ancien, and Schlumprecht in 2018, using a very elegant argument, which I like a lot. And a typical counterexample is the space, the original space constructed by Tserilson, not the space which was constructed by Figel and Johnson later, which is also named Tserilson space. Because that space, which is Figel and Johnson, it has an unconditional basis and has a non-trivial K-type. So by previous result, one can embed coarsely. One can embed L2 coarsely into it, but it cannot be embedded into the original, as these people proved. So I would like also to mention some other direction of research which are not of this type, but related to Dvoretzky theorem. One of the most important directions related to Dvoretzky theorem is finding optimal estimates for this function. And many aspects of this problem have been investigated, starting with a famous paper of Millman in 1971. And another is that starting with the paper of Bourgain, Figel, Millman in 1986, a parallel theory for metric spaces was developed. In this theory, the main goal is estimated from below the size, defined either as cardinality or in some measure theoretic ways, of subsets of a metric space which admit low distortion embeddings into a Hilbert space. And so it started in paper, as I mentioned, by Bourgain, Figel, Millman in 1986, but it became very active somewhat later. And after the fundamental paper of Bartal, Lineal, Mendel, Naor. And also there was a preceding paper in computer science where results of this type was applied to computer science. And one can find a short survey in section 8 of Naor's paper, of Naor's survey on Ribet program, which was published in 2012. So now we shall turn to our theorem. So what can we find in any infinite dimensional Banach space? So we are proving something about any infinite dimensional Banach space. So what can we find there? Dvoretzky theorem that implies that in any X, there are arbitrarily large subspaces which are arbitrarily close to Euclidean spaces. And I'm sorry. Using Mazur's techniques for constructing basic sequences, one can organize such almost Euclidean spaces into a rather decent finite dimensional Schauder decomposition. It is a standard technique which was introduced, I believe, by many authors when they needed it. So I cannot say about who did it first, that Mazur's technique can be applied to finite dimensional decomposition. It is a kind of easy to see. So we can organize a reasonably good In one direction, projections will be 1 plus epsilon. So it will be a good finite dimensional Schauder decomposition, which I shall write as FDD. So rather than this, and that means that we can require projections to have norms close to 1, and we can require even a bit more. So let us look at a locally finite subset M of L2. We can assume for simplicity that 0 of L2 is there. We can either add it because we still want to embed the obtained, or we can shift it, but in any case, it will be kind of convenient, and it is clear that it is without loss of generality. So now if we consider finite balls, and I did not write it here, but I consider balls centered at 0. So of course, each ball of finite radius spans a finite dimensional subspace of L2. It follows immediately from definition of locally finite metric space. Locally finite metric space is such that each ball contains finitely many elements, and therefore, of course, it spans finite dimensional subspace. And we consider indefinitely increasing sequence of radii, and we consider increasing sequence of balls centered at 0. I did not write here, but centered at 0. And then we will get an increasing sequence of finite dimensional Euclidean spaces. So the first space spanned by the smallest ball, the second by larger, and so on. And it will be convenient to denote the corresponding sequence of radii by rho 2i minus 1. It is just odd subsequence of increasing sequence rho k. So it is a natural idea. A natural idea is to find FDD of this form. So we just for each this space. Of course, it is possible to find an FDD in which this is. But of course, it will not be isometrically, because Fi are isometrically Euclidean, and an arbitrary Banach space does not have to contain isometrically Euclidean spaces. For example, a space can be polyhedral, like C0, and any ball of a finite dimensional space is a polyhedron, so it is not isometrically Euclidean. But by Dvoretzky theorem, it can be almost Euclidean up to any epsilon we want. So the space X does not have to contain such FDD isometrically, but it contains such FDD up to a linear map of an arbitrary small distortion. So what can we try to do with this? So now when we have such spaces, we split M into annuli. So AI, annuli number I, is the set of points with distance to 0 between rho I and rho I minus 1. And we let rho 0 to be 0. So the first annulus will be a ball rather than annulus. And rho I is so rapidly increasing. It is one of standard and natural ideas that we consider rapidly increasing sequence of these positive numbers, that if the embedding will almost preserve the norm of elements, to compute the distortion, it can be enough to consider pairs which are either in the same annulus or in neighboring annuli. Because if we consider points which are in annuli with gap, then one of them has very small norm and the other has very large norm. And so the estimate of distortion follows from triangular inequality and is trivial. So it is why we will consider rapidly increasing sequences. So we can try the following. we can try to map some. It is technically convenient not to. Okay, let me just read what I wrote. We can try to map odd annuli with odd indices into Fi by the natural isometric embedding, because Fi is spanned by a set containing. Fi, let me recall that Fi is spanned by ball of radius rho to I minus 1. Therefore, it contains A to I isometrically. And after that, we can try to bend somehow complementary even numbered annuli between Fi and Fi plus 1 in the direct sum. So one can just imagine that we have some annuli of with odd indices, we map isometrically into those spaces. And what annuli which are between, we shall try to bend between those spaces. And the problem here is that we need bending with distortion arbitrarily close to 1. And as you might guess, that it is not an easy task, because in an arbitrary Banach space, we don't have control on close to isometric level over these direct sums. We have some control. They can be a kind of close to being direct sums with small projections, but it is not close to isometric level control. And so this will be the main problem. We implement in our paper this construction. It is every notation is a bit different because there are some technical problems, but the main idea is this, that we consider annuli with rapidly increasing radii. We map even numbered or odd numbered into Fi, and we map what is in between, we bend between. It is how we will do it, but the main problem, of course, in this bending, how to bend it so that it will be very close to isometric. It is the main difficulty and the main problem which we're working on. So first let us define bending. We define it in more general way than we really need, but maybe at some point we will need more general. So let X and Y be Banach spaces, such that there exist two linear isometric embeddings of Y into Banach space X, and with distinct images. And let's see be a number between 1 and infinity, and a mapping Y from Y to X is called a C bending in the space X of Y in the space X from I1 to I2 with parameters R lowercase r capital. If it is C by Lipschitz, such that the restriction to the ball of radius r coincides with the first isometric embedding, and restriction to exterior of the unit ball of the ball of radius r coincides with the second. So it somehow really does what I implicitly described on the previous slide. It bends from the first isometric embedding to the second. And when we consider C bending of Y in the space, which is just direct sum of Y with itself, we restrict our attention to the case where I1 is just isometric embedding onto the first summand, and I2 is isometric embedding onto the second. And we call such bending a C bending of Y in the space Y plus Y with parameters R lowercase and R capital. So now, first steps in study bendings. In our paper with Ostrovskii in 2019, we constructed 1 plus epsilon by Lipschitz bendings of Y in the space or where Y is in the space Y plus Y with respect to LP. So sums with respect to LP, and P is, it can be 1, but we did not work with infinity. We did not need it. And we did not use the word bending. And that construction is based on the well-known in geometry notion of logarithmic spirals. For us, it would be very convenient to have a result on existence of 1 plus epsilon bending with some parameters r for every direct sum of the form y plus y with direct projections having so norms 1. With such a result, we don't really have norms 1 in our construction, but we can modify it a little bit and we will have what we need. With such a result, we would continue the argument about this direct sum, this finite dimensional decomposition, which we started above. So if we would have such result, we would just continue immediately and finish it. However, such result does not hold. And theorem 2 is there exists a 4-dimensional Banach space X satisfying the conditions. It is a direct sum of two-dimensional Euclidean spaces, y1 and y2, with direct sum projections. I mean projection onto y1 with kernel y2 and the other one. Having norm 1, there exists epsilon such that for any pair, no matter how we choose r and r, of course, we need to make them positive, this positive and at least in any isometric embeddings, there is no 1 plus epsilon bending. So there exist cases when the sum is direct. One can show that if the sum is direct, we can find bending with sufficiently large constant. Constant 5 probably will work for all direct sums with projection 1, but we need 1 plus epsilon. And so this is what we proved. It is our second theorem that there are very simple, in some sense, cases where there is no arbitrarily good bending. So now sketch of this proof. So we construct in the following way. First, we consider this is 4-dimensional Euclidean space. We consider it as a sum of y1 and y2. And we cut from the unit ball of this space finitely many zero-symmetric pairs of open caps. So, I mean, because we want it to be a ball, if you cut one cap, we need to cut a symmetric. This is why we consider pairs. And by a cap, we can mean the intersection of the ball with half space. And in such a way that nothing is cut from the balls of y1 and y2. So we don't touch them. As they were Euclidean, they stay Euclidean. Something is cut from any other two-dimensional space. And the ball of the resulting 4-dimensional space is close to the ball of L2 4 in some natural, of course, in Banach-Mazur distance too, but also in some more natural geometric sense. And as a consequence of properties of X listed above, for any gamma, there exists epsilon such that if Banach-Mazur distance of a two-dimensional subspace of X from L2 two-dimensional is very small, then the space should be close either to y1 or to y2 in the Hausdorff distance between unit spheres. It is a rather straightforward thing to prove. So now we assume that there is a 1 plus epsilon bending of X into that. By the Rademacher theorem, this map is differential almost everywhere. And using the standard argument, we get that at each point of differentiability, the derivative is a 1 plus epsilon by Lipschitz linear embedding of y into X. It is a standard thing that if you differentiate by Lipschitz map, the derivative will be also by Lipschitz with the same constant. And by the last item of in the previous site, I mean this blue item. Blue item shows that each subspace which is close to L2 should be close to either y1 or y2. And So by the last item, the image of this embedding is close to either y1 or y2. Combining this with the fact that X is not far from Euclidean space, we get that T cannot be 1 by Lipschitz. It is a kind of rather simple geometry, that because it is close to Euclidean, if you go to direction to y1 and in direction of y2, then it cannot be by Lipschitz. And of course, we need to play with some more or less standard real variable argument to get a suitable interval on which half will go into half will go into y1 direction, half into y2, and therefore it will fail to be by Lipschitz. So it is how we show that there is no bending ever close to isometric for general direct sums, even with constant 1, and even if the space are Euclidean. So conclusion, we need to do more work on the FDD to achieve 1 plus epsilon bending for an arbitrary small epsilon. And our first step is the following generalization of results which we published in 2019 about LP sums. And in the statement of our theorem on the next slide, we use a parameter CZ, which depends on geometry of two-dimensional space Z, and for which we have an estimate. So there is some parameter, I don't want to introduce it now, which depends on two-dimensional space and which is between 4 and 2 over pi. We did not try to get good estimates. These are enough for us. So this is bending in one unconditional sums. So if you have sum of y with itself, which is not just any sum with good projections, but with respect to one unconditional basis, then there is a bending with arbitrarily close to 1 by Lipschitz constant. So and again here, we assume that it is finite dimensional and let Z, for which the unit vector basis is one unconditional and normalized. So it includes, of course, two-dimensional LP, but it contains many other spaces. Then for every epsilon and every pair R of positive numbers satisfying this condition, logarithm comes from the fact that we use logarithmic spirals. So it is here is epsilon which we want to achieve. Here it is this constant depending of that two-dimensional space which you saw on the previous slide. And here is what we want. We want logarithm of the quotient to be sufficiently large, because if you move epsilon to that side, it will be in the denominator. So the closer epsilon to 0, the larger logarithm we want. So if you pick this number this way, there is n1 plus epsilon over 1 minus epsilon bending of y into the sum with parameters r and r. Furthermore, this bending satisfies the following conditions, which are important for us. First, that it is norm preserving. And second is just the way in which we get 1 plus epsilon 1 minus epsilon bending. So it is what we proved. And so how, I don't really want to go through estimates, but how we define the T. So let epsilon and r be any numbers. For real numbers T more than r, we introduce this function. So it is the same function which we use in definition of capital R, but it is now with parameter T. So now we introduce C of x, which is where this formula comes from. This formula comes from logarithmic spiral, because in logarithmic spiral, we have formula where we have cosine of logarithm and cosine of epsilon times logarithm. It is exactly what we will get here if we plug T into this formula. And here is just for normalization. And S of x, I just did not have enough space to write. S of x is similar function with 0 and 1 interchange, and cosine replaced by sine in the numerator. So here, instead of cosine, we have sine. Now let E be the identity map of Y into the first summand, and F be the identity map of Y into the second summand. So here is how we define T. So up to R, it will be in the first summand, because up to R, C of X is 1, and S of X will be 0. Then it will somehow go between on logarithmic spiral in all directions. This is what it will be, logarithmic spiral in all radial directions. And then after X, norm of X reaches R, this will become 0, so this term will disappear, and that term will become 1, because 0 and 1 are interchanged. So it is exactly what we want. An estimate for a Lipschitz constant is it is not very long, but it is a 2-page computation. We consider some cases, we prove some inequalities, and so on. So it is the first thing which we use. And now we have to look at FDDs for which sum of neighbors are unconditional or very close to unconditional. I mean epsilon unconditional. Note that such FDD don't have to be an unconditional FDD, because we ask only pairs to be unconditional. We don't need the whole FDD to be unconditional, because of course it is not possible in an arbitrary infinite dimensional Banach space. And here we use the following result, which is our theorem 4. Unconditionality for sums of Euclidean spaces. So let me go over this result. It is the most difficult result in the paper. I mean, final estimate is also difficult, but it is the second. So given any n, epsilon and a, they exist normally very large number n, such that if for every direct sum where these are isometric to very large Euclidean spaces, and direct sum projections having not so large norms, this is actually not that important condition, but okay. There are finite dimensional subspaces in X1 and X2, such that the sum with the norm induced from X is 1 plus epsilon isomorphic in a suitably defined sense to direct sum Y1 plus Y2 with respect to one unconditional basis. What I mean by suitably defined, that it is not isomorphic in any sense. It is isomorphic in the following. Y1 is mapped isometrically onto Y2, and Y2 is mapped isometrically onto Y2. So 1, 1 onto Y1, and Y2 onto Y2, and then this map will be 1 plus epsilon isomorphic embedding, isomorphic mapping. So after that, after we do it, we almost follow the plan outlined at the beginning, adding some necessary technical details. Because let me recall that by Dvoretzky theorem, we can have in our FDD arbitrarily large Euclidean space. Then by this result, we can make them smaller, but now the sums will be close to unconditional. And that's it. Then we use result on bending, so we can bend in them. And then we use the construction. There are some technical problems which we need to overcome, but the main idea of the whole thing is, as I just outlined, that we construct FDD with huge spaces. From them, we make small spaces, but still increasing in the way we want, because we want them to increase as those subspaces Fi. The resulting spaces we want to increase as spaces Fi in our original definition of them. Fi were defined as linear spans of finite balls of finite radius in that locally finite subset of L2. So now about proof of this result. So very looking for unconditional subsum. We restate unconditionality in the following terms. So let be a direct sum in which the subspaces are Euclidean, and let epsilon be in 0, 1. The sum is endowed with a norm whose restriction to y1 and y2 are Euclidean norms. And we say that this direct sum is epsilon invariant if for any orthogonal operator on y1 and on y2, we have this inequality. So if we rotate y1 in its subspace and we rotate y2 in its subspace, we get something which in norm is not very far from where it was. So it is our definition. And first lemma, if the sum is 0 invariant, if this is just equal, it is a sum with respect to a one unconditional basis in two-dimensional space. And I feel that it is a kind of rather special for Euclidean spaces, because Euclidean spaces have transitive norm. And it would be very interesting for us to have any analogs of this theorem, Theorem 4, for other spaces like LP or something like that. But at this moment, we don't see anything like that. So instead of working with unconditionality, we prove this lemma, introduce this definition, prove lemma about 0 invariant, and also another result, which is a kind of, also this result is, lemma 2 is simpler than lemma 1. So if it is epsilon invariant, it is 1 plus epsilon isomorphic to 0 invariant. So it is, we can do it in terms of invariance. And so now we search for epsilon invariant subsum, and it is a multi-step construction, which starts with the following. So it is our proposition. So we start first with a space where one, which consists of direct sum of two things. So it is isometrically Euclidean space and some one-dimensional space. And we can consider the sum as reasonable, so that norm of projections are equal to 1 in both directions. Actually not 1, it can be some larger number, but the norm of projections are good. And we want it to make it invariant over rotation in the Euclidean space. And of course, it does not have to be. If you have just Euclidean space, we build on it one-dimensional space with an arbitrary norm, reasonable norm. It can be whatever. I mean, it is not close, it is not far from Euclidean sum. One can easily estimate the distance, and it is not large. But we need a 1 plus epsilon estimate, so it is more difficult to do 1 plus epsilon. And it is how we start. We consider a space which has a one codimensional subspace y0, which is isometric to L to n, and its complement is a linear span of some vector x1. Then we can find in this y0, we can find space which is smaller, but controlled dimension, such that the norm of this alpha is just an arbitrary real number. The norm of alpha x1 plus y is epsilon invariant with respect to orthogonal operators. So we have one-dimensional space, and we have this Euclidean subspace. If you consider any vector from that one-dimensional space, I'm sorry, it should be x1. It is difficult for me to write it here now, but this should be x1, and not x. Because if I try my pen, it will not write here. Yeah, it does not write. So alpha x1. So it is rotationally invariant over subspace in the base for anything. And the original space does not have to be like that. There will be some constant. And here the only way which we invented is to use the result of which goes back to Larman and Money in 1975, and which was later with better estimates and shorter proof published by Yehoram Hardon in 1988. And so we do it in the following way. We consider many levels in this. This is like cone, but it is not spherical cone. It is some strange cone. At the bottom, it is Euclidean space, and at the top, it is 1 point. And so there is something between, reasonable. So we cut it on some level, and that on that level, there should be an almost spherical section. And we forget about everything else of the space. We consider only space for which there will be an almost spherical section, up to that epsilon or up to some other epsilon. So it will be already a better cone. And then we continue it on a discrete sequence of levels, which depends on epsilon. And the number of levels will be like 1 over epsilon. And if we do it on almost all those levels, if we make it almost spherical, then what will happen to dimension? According to estimates of Gardon, which are precise up to values of constant, each time it will be logarithmic. So we shall iterate logarithm 1 over epsilon times, but still it is controlled dimension. It is what we say and what we mean. But it will be ridiculously small for any, say, computer science problems. It will be an acceptable estimate when we take logarithm of the original dimension and 1 over epsilon times. But we, after doing this, we will get dimension where it is spherical on large collection of levels, and then using some geometry, we extend it to all other levels. And then it is only 1 cone. Then we need to do it for epsilon net. We need to do it in both directions, and it will mean that we iterate logarithm some more times, but it will be finitely many times, depending on something like of some order 1 over epsilon times. And then we implement that argument which I outlined above. Then we are able to implement, because now we have unconditional sums. And also there is one more trick, because in this unconditional sums, we don't want to do them two-sided. We don't want to apply this argument in one direction and in the other direction. So we don't want to apply it to F1 from one side and from the other. So between, we just use Dvoretzky theorem and do what we want. So it will be one sum with respect to unconditional basis obtained using this argument. One sum is just by applying Dvoretzky theorem, and then so on. And then we go with the argument, and that is what I wanted to say. So now, any questions?
Thank you, Mikhail.
Okay. So, Mikhail, that's very interesting about that one unconditional sum. I mean, of course, what's much easier, that's if you only wanted it suppression, one unconditional, that's much easier. But that's not sufficient for your remaining argument, right? That's the problem.
Yeah, because the basic step in bending, is that we need we need somehow it depends to depend only on norms.
Only on norm, yeah.
We cannot do it if it. So we don't see how to generalize it further. How generalize it further when we don't have. Because in the first step when we decompose this difference of t, tx and ty, we need. And I'm sorry, but what do you mean by suppression unconditional? It means that
just that both the projections are norm almost one.
no, that is not enough.
That's much too weak for what you need to do, and that's
Actually, what we need is the following. If you have two numbers such that the norm in Z of Z is 1, and we multiply them by vectors of the same norm, then the norm of the result will be the norm of that vector. This is what we need. We need that if you have, to say, AB, which has in Z norm 1, if you multiply them by two vectors which have the same norms, one in two vectors, different vectors in Y, but they have the same norm, then the norm of the result will be the norm of that vector.
mm-hmm.
This is what we need to proceed with our estimate.
Hi, Mikhail. Can you hear me?
Yeah, I can hear you, but I don't see you.
You don't see me. I'm
Yeah.
there.
If you change your view, you can see. Change view to gallery, you can see.
Okay, but still I have only 6 people.
Well, then imagine what you'll look like.
Yes, you can just imagine.
It is Jim Hagler.
Press the arrow to scroll to see the next 6 people.
I see. No, but Jim Hagler was talking. Or
No, this is Gilles L'Ancien.
Gilles, I'm sorry. Yeah, now I see you.
Okay, thank you very much for this very nice talk, and congratulations for this great result. So I guess the next open question is to know whether if a space contains uniformly the LP ends, does any locally finite subset of capital LP 1 plus epsilon embeds into X?
Yeah, the next probably is LP, but in general, one can of course ask it for any X. If say, if X is, no, for any say Z, if Z is finitely represented in X, and we have a locally finite subset of Z, then whether it 1 plus epsilon embeds into X. The difficulty which I see as the main difficulty will be in these unconditional sums, because we use the fact that it is Euclidean a lot. And also say for other spaces like LP, if it is, what is rotation invariance in LP? You need to consider isometries, but then it will not imply that it is a sum with respect to unconditional basis, as I understand. So it becomes much harder. If you go elsewhere, if you just depart from Euclidean.
Okay, thank you.
You're welcome.
Yeah, well, even if you want just the, instead of what you want, if you wanted just what I mentioned, just to get suppression 1, you know, where both the projections are norm 1, even that's okay for LP, but I don't know about more general than that. And it's for LP, it's more difficult than to do it for L2.
So you say that you know results where if you consider a sum of two Euclidean spaces OLP, then you can find a suppression unconditional space.
Yeah,
with-
you can make a suppression almost one unconditional because, well, you can use the Mazur technique first in one side, and this goes to a small codimensional subspace the other side, then do it on the other side, and you get a small codimensional subspace of what you have on the first side. But then you need to know that inside of what you end up with, you still have an LP ball of some significant dimension. And that's true, but not as elementary as the Hilbert space case.
Yeah.
So you have to use a very large, okay.
Yeah, we decided to publish it in this form because we don't see how to generalize it in a substantial way.
Is it possible to do for three sums? Like three spaces?
I mean, what do you mean?
Direct sum of three spaces.
You see, first of all, it will create some difficulties, but we don't need it.
I know you don't, but I'm just curious as a linear result, like whether.
No, you see, you can do it, say somehow on both sides. So you can see the three spaces, and you want all three sums to be unconditional.
No, so it's different, right?
No, it is to do it unconditional on one side and on the other side is possible, or just you iterate it twice. But all three, I did not think about it.
Okay. Okay, any other questions or comments? If not, thank you so much, Mikhail. That was really, really interesting. The paper also looks very interesting. There are a lot of pictures, so I suggest people take a look. So
Thank you for advertising.
Yeah.